Welcome to the short video on post-processing using Phoenix FEM. My name is Raja Raja, Director of Courses Provider, formerly a geotechnical professor at Johns Hopkins University. I would like to describe the details of post-processing with respect to this problem. Two sheet pile walls are driven into the soil, and the soil in between the sheet pile walls is excavated up to a certain depth. It's excavated in 4 layers, or 4 lifts as they are called in Phoenix FEM. It is of interest to model not only the deformation but also the pore pressure and the seepage. To post-process, you have to restart Phoenix FEM from scratch. To get to the post-processing interface, you click on the Continue button first, click on the General Use button, and then click on the post-processing button. You are in the post-processing interface. The first thing that you do is you type in the number of jobs that you have used for this problem. For now, I'm going to type 1, but if you do have more than 1 jobs, then you type in that number in this box and click Enter. The second thing that you do is you click over here and select the work folder and select the file which has an extension OUT and the job name that you are interested. So in my case it's sc51.out. Alright, so some information concerning the output files have been defined, the name and the directory. The rest of the output files would be brought into the memory on an as-needed basis. There are 3 things that you can do with this post-processing interface. You can examine the content of the files either by clicking over here or by going to the View pull-down menu and clicking on the Output Files tab. All of the output files that have been generated for this job would be listed in this box right here. Let's click on the file with the extension OUT. This is what we call the general output file. This file has lots of information including the coordinates, connectivity, iteration details, and so on. The file with the extension DIU has all the nodal data, including the displacements and the pore pressures, and so on. So there are several other files, like DIP has the nodal forces, DIV has the velocities, and DIW has the accelerations, and so on. So let's close that. The second thing that this graphical user interface would allow you to do is it would compile all the time history output, organize them, and present them in a Microsoft Excel workbook for you. We'll come back to that in a second. So obviously you have to have the Microsoft Excel installed in your computer to be able to utilize that feature right there. The third thing that this graphical user interface would do is it would allow you to plot mesh and selected responses, displacement responses, and will also allow you to animate selected responses including deformation, pore pressures, stresses, strains, and what have you. So we'll come back to in a second too. So let's click on this button, the time history output button. It'll take you to a couple of different forms here. First, the Microsoft Excel workbook will open, and then a few seconds later you will see, so let me just minimize this, you will see a little grid behind that. This grid basically is the key to the data in the Microsoft Excel workbook. These are the sheet numbers and these are the column numbers. Like for example, sheet number 1, column number J has the displacement in the Y direction at location number 1. Now this location number 1 is this one right here. So it also creates this graphical window with the locations of the output data indicated. Now this may not be very useful for you, although it could in some cases, because the Excel workbook itself has a detailed key for you. So let me go back to the Excel workbook, and different sheets have different information. So let me click on sheet number 1, and this one has the nodal data. Basically it has the displacements and the pore pressures, and this is the area that has the key. For example, column number H has the displacement in the y direction at a node which has coordinates given by these numbers right here. X coordinate is 10.63, y coordinate is 12, z coordinate is 0, because this is a plane strain problem. Now it's up to you to make use of the data as you see fit. You can plot, you can create some plots, or you can just save it and come back and work on it later on, and so on. So let's just go ahead and plot column F against column G. What you see here is the progression of the horizontal displacement at the top of the sheet pile wall during the analysis. As you can see, that the horizontal displacement has reached a value of about 2.3 centimeters at the end of the analysis. So likewise, you can go to any of these other forms and process the data as you see fit. So let me just close that. And we go back to this grid here. So click on this backward navigation arrow to get back to the main post-processing form. Alright. So let's click on the third button right here. Alright. And this form allows you to choose which of the two tasks that you want to perform. If you click on the first one, you can plot the mesh and select the displacement responses. If you click on the second one, you can animate the data. So let's click on the first one. Alright. This is one of the first form that we have encountered so far that has a button called the Start button. So you have to click on this button in order to bring the relevant data into the memory. Again, you wait for the blue bar to disappear before you proceed further. The data is in. Now you can start plotting. Let's click over here to see the mesh plotted, and you can choose the responses to be plotted from either one of these pull down menus. This is based on response numbers, this is based on increment numbers, and this is based on time. So I'm going to use this pull down menu and choose, let's just say, response number 85 to be plotted. And if you had chosen too many responses and you would like to remove some of them, you use this pull down menu to remove it. The default magnification factor is 1. Let's just go ahead and plot the response and the mesh using that default magnification factor. You can see that the magnification factor is not large enough to really see the response clearly. So let me just close this, go back to the form, and change the magnification factor to 10. Now you can see, you can distinguish the response from the mesh. Alright, so that's how you plot the mesh and the deformation responses. Let's go back using this backward navigation arrow. Click on the animation response button. And this is the other form that has a start button. Let's click on that. It didn't take too long because the data necessary to plot the animation has already been brought in as part of plotting the mesh and the response. So it's already in there. Alright, so you see a number of things on this form here. You see a lot of properties associated with the animation over here, and the default parameters used for them are also listed. You can change any of those. You choose the type of response that you would like to see animated from this pull down menu here. Default is deformation, but you can choose pour water pressure, stresses, strains, fluid velocity, and so on, if they are available. Some of those may not be available for the problem at hand. For example, if you are doing a drained analysis, pour pressure response will not be available. Alright, let's just go ahead and animate this using the default parameters. So you click on this animate button. It will take you to the graphical window, and you click on the start animation button. Here is the animation of the contours of excess pour water pressure. You can observe the formation of the steady-state equipotential lines at the end. This concludes this video, and thank you for watching.